Okay, very exciting. It's moving in straight lines. So previously, um, this is hard to explain. So in a normal Cartesian robot, like my 3D printer, for example, we've got X, which is this axis, Y, which is this axis, and Z, which is up and down. So each one of those three axes moves in a straight line, and they're all independent of each other. I can use this stepper motor here, and I can tell it, hey, turn 100 steps, and that will only move the x-axis a certain distance, which we can easily calculate based on the pitch of the belt and the number of teeth on the pulley and the number of steps on the stepper and the micro-stepping in the stepper driver and blah, blah, blah. It's not very hard. So all the axes are independent and they're all linear. A SCARA robot like this is an absolute pain in the ass because every axis moves every other axis effectively. So the angle of this affects the angle of this, and both of those angles affect the end point. So it means that if you try to move between 2 points, so for example here and here, you can calculate the angles required to get to that point, and you can tell and say starting angle here, end angle here for that arm, and then starting angle here, end angle here for that arm. And so you add both of those movements together and Bob's your uncle. You've got a start point, you've got an end point. Unfortunately, it's actually a very difficult problem to solve, possibly generally, or possibly just for me, to get this to move in a straight line, because it wants to move. If you just say, okay, step 1, I know you're at this angle, go to that angle. Step 2, I know you're at this angle, go to that angle. And it calculates the number of steps in order to change those angles. And then it makes that change. But what you'll find is that this won't move in a straight line between them. It'll go like, wow. It'll move in an arc. I'm obviously exaggerating, but it'll move in an arc between those 2 points. Because it doesn't know the kinematics of the system. It just goes to 2 angles. And those 2 angles changing at a constant rate will result in the endpoint moving in an arc. And if you want it to move in a straight line, say if you're writing some text or something, it might look nice still. I can get away with a lot because this is just an art project, but if your 3D printer was using a SCARA system and it sort of made arcing motions, that would be a showstopper. That would mean it wouldn't be able to work. And so I wasn't really too concerned about that for this thing, because it's just drawing art. If your letters are a little bit bulgy, who cares? But the problem arises when you're moving near the edge. So say we're way out here near the edge, and we need to move over to say there. If we move in an arc, it's going to want to swing out past the edge here, even though the bounds checking ensures that we're inside here and we're inside here. We can quite easily swing out past the edge of the enclosure because we're not moving in a straight line from here to here. We're going to naturally want to go and swing out because that's the most efficient move. That requires the least amount of angular change. So what I've had to do is solve that problem. So there's several approaches to this, most of which require too much maths for me to handle, given that it's been 15 years since I did any serious maths at uni. So my original thought was, what I'll do is, if I need to move from here to here, what I'll do is I'll break it up into a number of segments. That way each segment is sufficiently small, and so while each segmented move is going to arc a little bit, the distance is so small that the arc is not going to be significant. It's going to be close enough to a straight line. So as opposed to going, whoa, a big arc to there, what we'll get is little arc, little arc, little arc, little arc, little arc. And the difference between the straight move and the arc move is going to be much smaller for a small move. And then I thought, that's going to be garbage. That's just going to be an approximation to the path. That's not a good solution. I really should do it properly. And so I thought for a while about how to do it properly, how to handle that maths. And I gave up. I was like, this is all too hard. So I went and had a look at some resources online for how to do that maths. And I found some articles that were like, this is a really hard problem. One of the most popular solutions is just to break the path up into smaller steps. I was like, that's good enough for me. So right now this is not moving in a continuous motion, it's moving in 1 millimeter short moves, and it's chaining them together. And so if it's moving, it's at about 200 mil move, it's actually moving 200 little motions. And so the G code just says G1 X100 Y100, and then X negative 100 Y100 negative 100 negative 100 100 negative 100, then back to 100 100. So there's no intermediate points in the G code, but the software interpolates as many intermediate steps as is necessary, such that no move is any longer than 1 millimeter. And I can go lower than that. I probably will, just for a test, because you can see it sort of jittering slightly. Not really too concerned about that. I mean, the ball moving through the sand will act as a bit of a damper on this and will tend to smooth the motion out. Because this system's quite light, any jitter it sets up a resonance and starts wobbling around. But once it's actually got the ball on it and the magnet, I don't think it's going to be a problem. So the next problem to tackle is homing. So there's a case where, let's just wait for it to home. So when homing, that passed beyond the end of the enclosure. And there's no easy way for me to solve that with the tools I have to hand. So that's a mild problem. Because I don't have the enable pins connected to my stepper drivers right now, I think I'm going to have to do that. So I can disable the arm that is not being homed while it's being homed, such that if arm 2 crashes into the side, it'll just sort of floppily fold out of the way and let arm 1 home. However, it's possible for us to home arm 1. Actually, I'll power it up right now. I'll show you. Oh, oops! I didn't actually reset it then. Okay. Reset. Power on. So see that? It homes arm 2 and it passes outside the enclosure. So if it starts up in the wrong place, then homing arm 2 can also bonk into the enclosure. And that's a difficult situation because in that case both the steppers need to be active in order to hold arm 1 steady while arm 2 homes, and also arm 2 needs to be activated so it can home. So I'm going to need to think about some other options. I had a brainwave last night that I could attach a flag to the arm 2 drive pulley between the two belts, so the belt that connects to the stepper and the belt that connects to the driven pulley. I can have a little, just like a fragment of a Stanley knife blade or something jammed into the pulley, and then have an opto coupler, opto switch sort of right down in here, such that the blade poking out from between those two pulleys passes through the opto switch. But there isn't enough clearance for that, because we need about 5 mil to account for the height of the opto switch, like I mentioned recently. So the blade needs to pass through there, but then the arm 2 belt needs to pass above it. So we need quite a bit of a gap in there. I could put the flag on the underside of the arm 2 driven pulley, the arm 2 drive pulley, but like down inside this little crack between the arm 1 belt and the arm 2 belt. But there's bugger all clearance in there, and these heads are going to be in the way. I can countersink those. And the other downside of this approach is that the opto will be very close to the axis of rotation of this pulley, which means that its resolution won't be very good. Ideally, you want to get them all the way out as far as you can, so they pick up at the full range of motion. Yeah, I don't know. I've also considered, so you can get these opto switches, but a reflective version, so they have the emitter shooting out a beam of infrared and then the receiver pointing at that. And so if something reflective comes over the top, then the receiver can see the transmitter's infrared signal, and then you get a logical 1. You say, yes, there's something reflective here. And what I could do with that is I could paint a reflective dot on the belt and set it up here watching the belt. And because this belt only moves one pulley circumference when it's homing, I should be able to home it that way. But there's other problems with that. So, I don't know, it's an open question. I should be able to put the lid on, put some sand in the tray, and do some drawing pretty soon. I'm going to go to the hardware shop this afternoon and buy some polycarbonate lid I can put on top of this so I don't end up with sand all over my computer room. Okay, there's a long video.